Okay, welcome to this today's virtual lecture. Sorry that I'm not able to be there today. I'll be back next week to finish the course strong. I'm sure you're all sorely disappointed that we don't get to meet today, and so hopefully you can all cope with that appropriately. All right, so we're going to talk today about some of the beginning parts of Chapter 9, which is the last chapter we'll cover in this course. But before I get into that, I want to make a quick announcement about the next exam review. I'll give you some other reminders about this in the near future, but the midterm 3 review, so for the third and final midterm, is going to be held on Friday, April 20th. And that's going to be at 1 p.m. and still in the same classroom, SCC 100. Alright, so I hope to see you all there. That will be recorded as usual, so it'll be available on YouTube if you're not able to come. And the review sheet that we're going over should already be on Blackboard, if not today, very soon, so keep an eye out for that. And that will be something you can go through on your own ahead of time if you find it helpful to do so. So what we're going to get into today is material from Chapter 9. So we'll start with a quick review of what we finished with last time, which kind of set us up for what we're going to talk about in this chapter. And that's kind of setting the stage with differences between condensed phases and gas phases. So we talked about the gas phase extensively in Chapter 8. Chapter 9 is going to be sort of a hodgepodge of topics related to condensed phases, which are liquids and solids. And so what we have to first remember when we're distinguishing gases from condensed phases is one of the key assumptions from the kinetic molecular theory of gases was that these gas particles, either the atoms or the molecules that make up gases, have no interactions with each other. Alright, and so that was responsible for the predictable relationships we had between pressure and volume, and the idea that gases can be expanded or contracted to whatever volume we want, and the pressure and everything responds to it. In reality, that's not true. We kind of talked about that a little bit at the end of Chapter 8 with the idea of real gases and their deviations from the ideal gas law are because of this key assumption not exactly being true. And this really plays a role, as I said, in real gases, but also in liquids and solids. So in real gases or in condensed phases, the atoms and molecules are in constant contact with each other. So this idea that they don't interact is simply not true in these situations. And these interacting forces which hold them together are responsible for them existing as these condensed phases. So they don't allow the molecules to just completely separate and wander off all over the place. It's these forces that keep them together as a liquid or a solid. And what today's lecture is going to be about is sort of the nature of these intermolecular forces, as we call them, the forces that hold together separate atoms and molecules. In both liquids and solids, these intermolecular forces are very important. So let's talk a little bit more then about the definition of intermolecular forces and sort of a distinction between this and some of the things we've learned previously in the course. And what we have to really do a good job of internalizing right away is that these are forces of attraction between two separate atoms or molecules. Alright, so it's easy. One of the common sources of confusion in this part of the course is to sort of equate these with the bonds, the covalent and ionic bonds that we've already talked about, but these are forces of attraction between two separate molecules, I should say. Or two separate atoms. But keep in mind that the two molecules that are interacting through these intermolecular forces, or the two atoms that are interacting, are not chemically bonded to each other. So we're not talking about covalent bonds or ionic bonds or any of the other types of chemical bonds we talked about before. We're talking about these. We're talking about the force of attraction between two separate atoms or molecules. So let's make sure we're clear about what these intermolecular forces are not referring to. So as I said, they're not referring to chemical bonds. So when we're evaluating the strength of an intermolecular force, as we're going to be asked to do in this part of the course, we don't want to think about it in terms of the strength of the bond between two atoms. We want to think about it as a force of attraction between two separate atoms or two separate molecules. And so they have a very common mistake that people make is to think that a molecule that has a stronger covalent bond strength has stronger intermolecular forces, but these are two separate topics. So these covalent bonds that we've talked about previously in Chapter 3 are intramolecular forces. We didn't really use that terminology back then, but to distinguish them from intermolecular forces, that's what they are. So the Latin prefix inter means between, intra means within, and that's kind of the distinction we're making here. We're talking about forces between two separate molecules or atoms. So before we get into talking about intermolecular forces, let's get a quick primer on phase changes, because as I said, this chapter of the course deals with condensed phases, liquids, and solids. And one of the key effects of these intermolecular forces is that they influence these phase changes, these properties of interchanging between liquid and gas, liquid and solid, and so on. So one type of phase change we'll consider is the interconversion of a liquid and a gas. So if we go from a liquid to a gas, as we're likely all familiar with, that's called boiling. So when we boil a substance, we convert it from the liquid phase to the gas phase. And then the opposite process, maybe not as common a terminology, but one that you've still probably heard before, is called condensation. So when we take a substance from the gas phase to the liquid phase, we refer to that as condensation. And we're going to always, for these phase changes, talk about a temperature at which these processes occur. We're going to get a more precise definition for these phase change temperatures later, but for now, we should be familiar with the idea that the boiling point is the temperature at which the liquid and the gas interconvert. And we all know that this is true for water. We've all boiled water before. And so when you heat up water to a certain temperature, it boils, it goes from the liquid phase to the gas phase, and that temperature for water occurs right at 100 degrees Celsius. Every other substance is going to have its own unique boiling point associated with it, but at some temperature, the substance will interconvert between liquid and gas. And then we also can talk about the interconversion of liquid and solid phases. So as we all are familiar with, if you go from liquid to solid, we call that freezing. Now water doesn't freeze very often in Houston, but it can. Of course, if we go to 0 degrees Celsius, that's the freezing point of water. And then the opposite process, going from the solid back to the liquid, is referred to as melting. And so the temperature at which these occur is referred to as either the melting or the freezing point. Those are often used interchangeably. I think melting point is probably more common in a chemistry standpoint, but they're the same temperature. They refer to the same thing, which is the temperature at which the liquid and the solid interconvert. And so again, every substance is going to have its own characteristic melting point, which is the temperature where this process occurs. And there's again a more precise definition of this that we might get into later, but for now just know that this is the temperature at which the solid and the liquid convert between each other. And really the key concept in this part of the course, and why this is important when we talk about intermolecular forces, is that when you have stronger intermolecular forces, so a lot of what we're going to be doing is talking about the strength of intermolecular forces and how do we compare two substances to each other in respect to their intermolecular forces, which are abbreviated as IMFs. And so when you have stronger intermolecular forces, that correlates then with a higher boiling or higher freezing point. And that's then one of the key effects of these intermolecular forces. And I think this makes a little bit of intuitive sense, because the intermolecular forces are the forces which are responsible for holding the atoms or molecules together in a liquid phase. And if those forces are stronger, you're going to have to put more heat into the system or go to a higher temperature in order to be able to break those forces and separate the atoms or molecules into the gas phase. So I think that follows pretty closely from some things we talked about earlier with the differences between liquids and gases. And so the stronger the intermolecular forces, the higher the boiling point and the freezing point. Now let's get into talk about the types of intermolecular forces in kind of defining which substances have which types of intermolecular forces, because really our key task when we're comparing substances and talking about their intermolecular forces is going to be to figure out what is the strongest intermolecular force that is present in this substance, and that strongest intermolecular force is then going to dictate those phase change properties. So the first one we'll talk about is London dispersion forces, sometimes just called dispersion forces. And so what substances have London dispersion forces? And I guess I should be a little bit more clear to say this is all substances, not just compounds, but elements and compounds. And so which one of those have London dispersion forces? The quick answer to that is all of them. So London dispersion forces exist in anything that has electrons, which of course every substance has electrons that we're going to talk about. So anything with electrons will experience these London dispersion forces. And what it involves and why it occurs is what are referred to as instantaneous dipoles. So even in substances that are completely nonpolar, and those are the examples we're going to give here, you have what are called instantaneous dipoles that are responsible for some force of attraction between the molecules, even when there's no net dipole moment overall. And so the way that instantaneous dipoles work and the way that these London dispersion forces operate is that, let's say we have a monoatomic element like helium, so a very simple substance, and we know from earlier stuff that we talked about in the course that the electrons in helium reside in a 1s orbital. The 1s orbital is spherically distributed on average, and so on average we would expect the electron density to be completely spherical, completely equally distributed, and there would be no polarity associated with helium. It's a completely nonpolar substance. However, over some period of time, we have to recall that these 1s orbital that would give us spherical shapes, that's just the probability density over a 90% region or whatever region we define. So over some period of time, we're going to have distortion of the electron density. It's not always going to be spherical. It's going to distort over time, and then the average being a sphere. And so what that means is that we're going to have these instantaneous dipoles set up where the electron density is unequally distributed. So if we have our helium nucleus here, at some period of time we're going to get an unequal distribution of the electrons away from the nucleus, no longer spherically distributed, and that's going to set up a very small dipole, delta plus, delta minus, where the electrons are unequally distributed. This is going to influence a neighboring atom and is going to polarize it into the opposite way, where we're going to have an unequal distribution in the opposite direction, and these oppositely charged dipoles line up with each other and have some small force of attraction. And then again, this is a dynamic situation. It's not that it's going to statically reside like this, and so then the electron density over some other time scale will distort in the other direction, and you'll get, again, delta minus, delta plus, delta minus, and the two oppositely charged dipoles line up with each other. Sorry, I just don't know how to use my tablet. Alright, we're back. And so you get, again, these instantaneous dipoles, these little forces of attraction, because of the distortion of the electron density, which is not always going to be spherical. On average it's a sphere, but it's not always going to be spherical. And then the same thing happens in molecules. So if we have a Br2 molecule, let's say, as an example, we know that this is a nonpolar molecule because the two atoms that are bonded to each other are the same, so they have the same electronegativity. And so on average we'd expect the electron density to be equally distributed in Br2, because that's what it means to be nonpolar. You have an equal distribution of electron density. So on average there's going to be no dipole force of attraction, but just like we have in the example with helium above, this electron density is going to distort at periods of time. It's not always going to be symmetrically distributed. On the average it will be. And so at some period of time we're going to have an unequal distribution this way, where you're going to have more electron density on one side of the molecule than the other. You almost think about this electron density as sort of fluctuating between these two extremes. And so at this extreme you're going to get a delta plus and a delta minus, and if that lines up with a neighboring molecule that's polarized in the opposite direction, delta minus, delta plus, you're again going to get these weak attractions between the dipoles. But again, this is a dynamic situation, so the electron density will distort back in the other direction, delta minus, delta plus, and then if the other one distorts as well, you're going to get delta minus, delta Sorry, delta plus delta minus that way. Opposite dipoles line up and have a small force of attraction. So this is a hard concept to wrap our head around because we don't think of electrons as being unsymmetrically distributed when we have a nonpolar molecule. But we have to keep in mind that electrons are dynamic. They're not, as we know from orbital theory, they're not fixed in one place. There's a whole region of space in which they can exist. So there's going to be always some small probability of the electrons being distorted. And during those small periods of time when the electrons are distorted, there's going to be a small dipole, and then that's going to interact with other small dipoles that are present and give you these non-zero forces of attraction. I do want to emphasize that London dispersion forces are very weak compared to other types of inter- and intramolecular forces. They're extremely weak, but they're still nonetheless important in a lot of condensed phases and even in nonpolar substances. So let's talk about then how we compare the strength of London dispersion forces. So even if you have a series of substances that only exhibit London dispersion forces, so if we have all the noble gases, London dispersion force is the only type of intermolecular force that's present when the substance is nonpolar. But even in this series of substances, the London dispersion forces are not necessarily all going to be equal in strength. And so if we look at the boiling points of the noble gases, starting with the lightest one, helium, and going on down, helium has a boiling point of 4 Kelvin, so very low boiling point. You have to go all the way down to 4 Kelvin to get helium down into the liquid phase. Anything above that, it will be a gas. And then if we go for neon is 27 Kelvin, argon 87, krypton 121, xenon 165. And so we want to recognize this trend here, and we see that as we go to the heavier and heavier noble gases, the boiling points increase. So all of them are gases at room temperature. Even radon boiling point is below room temperature, which is about 298 Kelvin. But still, we see that the boiling point does sequentially increase. And so what we can conclude from this, knowing that higher boiling points implies stronger intermolecular forces, is that London dispersion forces are stronger when you have more electrons present, when you have heavier atoms involved. So London dispersion forces are stronger when there are more electrons. Or alternatively, you can think about it as when you have heavier atoms or molecules. Alright, and the reason for this is what's referred to as polarizability. So when we talk about polarizability, it's the ability of these electrons to distort, and we said that that's responsible for the instantaneous dipoles that we attribute to these London dispersion forces. So polarizability is the ability of an electron cloud to distort. And the reason that these heavier elements, heavier atoms, have stronger London dispersion forces is because in these heavier elements, the outer electrons are more polarizable. So as we talked about back in chapter 2, as you go to lower and lower rows in the periodic table with more and more electrons, you're going to fill subshells that are further and further away from the nucleus. And these outer subshells that we have in the heavier elements are going to be less tightly bound to the nucleus because they're farther away, and also then the electrons have a larger region of space that they exist in. The radial probability distribution for subshells also gets larger as you go down the periodic table to further and further subshells, more outer subshells. So for all of those reasons, the outer electrons are less tightly held in heavier elements. So in larger atoms, the outer electrons get held to the nucleus less tightly. And so that means heavier atoms are more polarizable. And so because they're more polarizable, you have more distortion of the electron density, and you're going to have stronger instantaneous dipoles and stronger London dispersion forces. Alright, so however you want to remember this, the idea is that when you have more electrons, when you have a heavier element, you're going to have stronger London dispersion forces. So let's do a quick sample problem. Let's rank the halogen molecules from lowest to highest melting point. And so what we have to do is write these out. And so the halogens are going to be, to review that, let's go to the periodic table. So the halogens are those group 7 elements, the second to last column of the periodic table. This periodic table going. Alright, so halogens are over here. Oh, I just closed it by accident. Disaster. Alright, so here's the halogens, group 7A. And so the 4 that we'll consider, the last one being radioactive, so let's ignore that one for now. We have fluorine, chlorine, bromine, iodine. We know that those all exist as diatomics. So let's try to rank their boiling points then. So we have, in the order that I gave, F2 being the lightest, then Cl2, then Br2, then I2. And what we know from what we just talked about is that stronger intermolecular forces correlate with a higher boiling point. Sorry, here we're talking about melting point, not boiling point, but it's the same concept. So the stronger intermolecular forces imply a higher melting point. And the only intermolecular force we have in these is London dispersion forces. These are nonpolar molecules, so that's the only intermolecular force present. It's going to be stronger in the heavier elements. And so then our expectation is that the highest melting point is going to be the heaviest one, the lowest melting point is going to be the lightest one, and so those melting points would be just ranked in the same order. Fluorine being the lowest, then chlorine, then bromine, then iodine. And this is exactly what you would see experimentally. And thinking about the standard states of these elements, we can see that the stronger intermolecular forces do exist for the heavier ones. So F2 and Cl2 are both gases, meaning they have very weak intermolecular forces. When you get to Br2, which is heavier, the intermolecular forces are stronger, and this exists as a liquid at room temperature, one of the only 2 liquid elements, as we said in Chapter 7. And then I2 exists as a solid at room temperature. So you sort of can see that progression of intermolecular forces as you go down the column of the halogens as well. Alright, so the next thing we're going to get to are what are called dipole-dipole forces. So this is the next type of intermolecular force that we're going to talk about. And sort of characterizing how strong these actually are, these are still only about 1% as strong as a covalent bond. So I want to keep emphasizing the point that these intermolecular forces that we talk about are much weaker than chemical bonds, but they're still important when we talk about phase changes and things like that. So when we talk about dipole-dipole forces, as the name suggests, these are forces that exist when we have molecular polarity. So any polar covalent compound is going to have dipole-dipole forces. And the thing we have to always keep in mind too is that we must have a molecule that has net polarity, not just polar bonds. Because we talked about in Chapter 4 how when we started talking about the shapes of molecules and how that relates to polarity, it's possible to have polar bonds in a molecule but no net dipole because of the geometry of that molecule and the cancellation of those dipoles. So it can't just have polar bonds. In order for you to have dipole-dipole forces, the molecule itself must be polar. So we're talking about only molecules that in total are polar. Let's talk about a simple depiction of this. So let's say we have the HCl molecule, another diatomic. In this case, we know that the electronegativities of the 2 elements are different. Chlorine is more electronegative than hydrogen, and so when we have HCl, we're going to have a permanent dipole, delta plus, delta minus, that exists at all times because of the unequal electronegativities of the 2 elements. And so if this lines up then with another HCl molecule that's oriented in an opposite way, we're going to get these interactions between the opposite charges. So if we have another HCl molecule down here, delta minus, delta plus, you can get this type of interaction between the 2 dipoles, where again the opposite charges attract each other. We can also have these sort of side-to-side interactions. So these dipole-dipole forces can exist in a lot of different directions, a lot of different orientations, but the idea is that we're lining up these opposite dipoles and having them interact with each other. And so same thing down here, that's going to interact with the chlorine, that's delta minus. and then these can interact with each other. So there's going to be these networks of these dipole-dipole interactions that exist in all directions. Now, one subtle point about this, which is not terribly important, is that there's also going to be some repulsive interactions. So the delta pluses, the like charges, are going to repel each other. So I'm going to draw in red these repulsive interactions. And then the Cls, which are partially negative charged, are going to repel with the other chlorines. So there's not just going to be attractive forces, but the molecules are going to line themselves up in such a way as to maximize the attractive forces and minimize the repulsive forces. So again, to draw that out, the blue ones I'm showing are attractions between oppositely charged dipoles. The red dashed lines that I'm drawing are repulsive interactions between like charged dipoles. Both of these are going to exist, but in net there's going to be an attraction because the molecules will line themselves up in such a way as to maximize those attractive interactions, and that's going to then lead to these relatively strong intermolecular forces, at least stronger than the dipole, or sorry, stronger than the London dispersion forces we started with. So that's what dipole-dipole forces are. And then the last type of intermolecular force, which is not really a separate type, is called a hydrogen bond. And again, this nomenclature gets a little bit confusing. We're not talking about a covalent bond involving hydrogen. We're talking about an intermolecular force, and these can be up to 5 to 10% as strong as a covalent bond. So we said that the dipole-dipole forces are only about 1% as strong as a covalent bond. These ones are, 5 to 10 times stronger than that, but they're still not nearly as strong as the bond itself. So these are still weaker than a covalent bond, but stronger than regular dipole-dipole forces. And so what these hydrogen bonds are is just a particularly strong type of dipole-dipole interaction that exists in certain molecules. So there's no fundamental difference between a dipole-dipole force and a hydrogen bonding force. They're the same thing, except that a hydrogen bond is sort of a special category of dipole-dipole forces. So when do we have hydrogen bonds? They're going to exist in molecules with HF bonds, which was basically just HF itself, OH bonds, or NH bonds. And again, these are not the forces associated with the covalent bond itself. These are forces of attraction between two separate molecules that have these HF, HO, or HN bonds. And the reason why we have these strong interactions is because these are all very polar bonds. So fluorine, oxygen, and nitrogen are sort of the three most electronegative elements. So when they bond with hydrogen, you get very polarized bonds to hydrogen. So a large dipole present in all of these. But also the other key point is that hydrogen is really small. So because hydrogen is really small, these molecules are able to sort of line up to each other really close. The hydrogen can sort of fit in and get close to the other molecules, and so you have these strong forces of attraction, and also they're able to pack closely together, which makes them even stronger. And so that's why these hydrogen bonds are especially strong compared to other types of dipole-dipole forces. So examples of molecules that would exist, or that would exhibit hydrogen bonding, would be, of course, HF itself. Water is probably the classic example, or the most well-studied hydrogen bonding substance. Alcohols like CH3OH, they have one OH bond, and so that would involve hydrogen bonding. And then if you have ammonia, NH3, something with NH bonds can also hydrogen bond. So all of these substances that have these really polar bonds to hydrogen exhibit what's called hydrogen bonding, which is just a special type, an especially strong type of dipole-dipole interaction. So those are the three major types of intermolecular forces. Now there are also some that involve ions, and I don't think our book goes into much with this, so we're not going to have a lot of talk about this in this chapter, but it will potentially come up next semester a little bit. So there are some forces involving ions that are even stronger. So one type is called ion-ion forces. These are the forces that hold ions together in a crystal, something we'll talk about later on in this chapter. So when you have two oppositely charged ions, they interact with each other very strongly, and these are classified more as a bond than as an intermolecular force. This is one of those sort of ambiguous categories. We call this an ionic bond, or we call it an intermolecular force. Generally, these are thought of more of as ionic bonds than as IMFs. But we should recognize, based on what we've talked about now, that if we have two charged species of opposite charge, so let's say Na plus and Cl minus, we have a very strong interaction between those. These are permanently charged species, and so that force of attraction is going to be very strong, and that's what we would refer to as an ionic bond, or sometimes as an ion-ion force. And then ion-dipole forces, which are very relevant in aqueous solutions that we talked about back in Chapter 6. These are interactions between polar molecules and ions. Sorry. And the classic example of this would be in aqueous solution. So when we dissolve an ionic compound or a strong acid in aqueous solutions, we know that there's going to be ions that are released into that solution. And these ion-dipole forces are a pretty strong category of intermolecular forces that are even stronger than dipole-dipole forces. So if we have water molecule, which is polar, as we know, delta plus, delta minus, the delta minus, the oxygen, can interact with a positive ion in solution like sodium plus, and you get this ion-dipole interaction where the opposite charges interact with each other. Or we can have the positive side of water, the hydrogen, so delta minus, delta plus on hydrogen, that can interact with the negatively charged ions like Cl minus. So this is the process that's responsible for dissolving ionic compounds in solution. And these types of interactions between ions and dipoles are stronger even than dipole-dipole forces. So I want to introduce this for completeness, although as I said, you won't really see this much at all in Chapter 9 because Chapter 9 just deals with intermolecular forces in pure substances. You'll get to, at the beginning of Chemistry 2, probably in Chapter 10, I would believe, you're going to talk about intermolecular forces in mixtures, in solutions and other types of mixtures. And so that's where these would come up in a greater context. So for now, we're not going to really deal with these two types that we talked about here as much, especially the second one is not present in any pure substance, but we're just going to be aware of their existence. So then finally, let's rank the intermolecular forces that we have. So let's talk about the ones that occur in pure substances. So as I said, when you have solutions, especially of ionic compounds, you can have some even stronger interactions that are important, but not for this chapter. So in pure substances, the weakest intermolecular force is the London dispersion force. Dipole-dipole is the intermediate one. And then hydrogen bonding is going to be the strongest intermolecular force. So this is the ranking of those from weakest to strongest. And as I said, really our key point, our most important task when we're doing these types of problems in this chapter is to be able to identify what is the strongest type of intermolecular force that's present in the substance, because it's that strongest IMF that's going to be responsible for the properties. It's going to overwhelm any of the effects of the much weaker forces that could also be present. Alright, so let's do some sample problems with this. Let's talk about CO2 versus COS. Which one has a higher boiling point? So when we're trying to compare two substances and determine which one has a higher boiling point, we need to determine which one has the stronger intermolecular forces. Because as we said, stronger intermolecular forces correlates with higher boiling points. So let's first consider the two molecules. And if we want to know what types of intermolecular forces are present, we need to know whether the molecule is polar or nonpolar. We can exclude hydrogen bonding already because neither of these substances have hydrogen at all, nonetheless any bonds between oxygen and hydrogen. But at the same time, we need to talk about whether they're polar or nonpolar to understand whether there's going to be any dipole-dipole forces. So if we draw CO2, we should know by now that CO2 is a linear molecule. This is one of the early examples we gave of a nonpolar molecule with polar bonds. So when you have CO2, you have partial negative charge on these oxygen and a partial positive on carbon, but the dipoles cancel each other out. So CO2, even though it has polar bonds, is a nonpolar molecule. And because it's nonpolar, we know that it has only London dispersion forces. So any substance that's nonpolar, if it's just a monoatomic substance like a noble gas, or if it's any sort of nonpolar molecule, it's going to only have London dispersion forces. Now let's talk about COS. So COS is still a linear molecule. We're just replacing oxygen with its heavier group 6 analog sulfur. I'm leaving out a bunch of lone pairs, so hopefully that doesn't bother anybody too much. But if we look at this molecule here, we still have a dipole pointing in this direction, but the carbon-sulfur bond is much less polar than carbon-oxygen. Oxygen is more electronegative than sulfur, and so a carbon-sulfur bond is very weakly polar. So the dipole going from right to left, as I've drawn it, is going to be much smaller. So this dipole doesn't completely cancel itself out, and you're going to have a net dipole pointing towards oxygen. Okay, so this is one of those situations where you have two dipoles that are not equal to each other, and so they don't completely cancel each other out. So this molecule is going to be polar. Okay, it's going to have an unequal distribution of electron density because the dipoles do not completely cancel each other out in this case. And so because it's polar, it's going to have dipole-dipole forces between the molecules. And so between these two molecules, you have London dispersion forces only in CO2. You have dipole-dipole forces present in COS, which is and those are the two strongest forces present in each of these substances. Dipole-dipole forces are stronger than London dispersion forces, and so you would expect this one to have the higher boiling point. Alright, so that's kind of how you want to talk yourself through these types of problems. Figure out what type of intermolecular force is present in the substance, and the one that has the stronger intermolecular forces is going to be the one that has the higher boiling point or the higher melting point, whatever the situation is. Alright, so let's move on then and talk about properties of liquids, which many of these are going to derive from these intermolecular forces that are present. And so if we go on to this section of the course, sorry, let me get my notes organized here. Alright, so let's talk about the properties of a liquid. And so we have a few things we want to talk about with respect to liquids. We're not going to deal a lot with liquids in this section. Most of the chapter deals with structures and properties of solids, but we're going to say a few things about liquids. And one of the things we want to understand is what's called surface tension, which is the resistance of a liquid to increase its surface area. That's kind of the precise definition. And as we talked about when we first defined what a liquid was a little bit earlier, a liquid always has an upper surface, so it can change its shape depending on the container it's in, but it always has an upper surface, and that upper surface is caused by what's called surface tension, is the resistance of a liquid to increase its surface area. Alright, and this is because of intermolecular forces that are present, and those intermolecular forces at the surface sort of keep the molecules from spreading out too much and result in that surface tension. And this is a property that you may have seen with water. So we know that stainless steel is more dense than water. It should sink if you put it in there. But if you take a really light piece of stainless steel, something that like a paper clip, for example, that has a large surface associated with it, you can put a paper clip on water and it'll float, at least temporarily, because of that surface tension at the top of the water. Now, another property of liquid is called capillary action. So this is the spontaneous rising of a liquid in a glass tube. So if you put a thin glass tube into a liquid, that liquid will rise up the tube. If you're from the UK, you would call this capillary action. We'll call it capillary action. And the reason this happens is because there are intermolecular forces between the liquid and the glass itself. And so those forces sort of pull the liquid molecules up the tube to some extent. And that's referred to as capillary action. And then when you have, these different properties in liquids, they're caused by two different types of forces. There's adhesive and cohesive forces. So the adhesive forces are the force of attraction between the liquid and the container that it's in. And this is especially prominent in glass because glass itself has a polar surface. So because glass is polar and because most liquids, especially water, are polar, you get this interaction between the liquid and the glass itself. And so that's what's referred to as the adhesive force. And then the cohesive force is just the intermolecular forces of the liquid itself. So the dipole-dipole forces or the hydrogen bonds, whatever strong intermolecular forces are present in that substance. So the cohesive forces are mainly responsible for the surface tension. These forces of attraction between the molecules create this upper surface, this resistance of the liquid to flowing or changing its surface area. And then the adhesive forces are responsible for capillary action. So both of these forces play a role in the two properties we mentioned. And then the other property of liquids is what's referred to as the meniscus of the liquid. So when you have the upper surface in a liquid in a container, it can be either convex or concave. Convex being that it's sort of buckled down, concave being that it's sort of buckled up like that. And so in a convex meniscus, you have cohesive forces are stronger than the adhesive forces. And so the liquid doesn't want to rise up the side of the container because it's more strongly attracted to itself. And then in concave meniscus, the opposite situation is true. The adhesive forces are much greater than the cohesive. All right, and because then when you have a convex meniscus, the liquid is rising up the side of the container because of the stronger adhesive forces between the liquid and the container. So these are just a few properties of liquids we want you to just know the definitions of. There's not going to be a ton of homework or test questions that deal with these topics because, as I said, we're not going to really learn a lot of the details of them. But let's talk about a few more properties of liquids that are also important. And one of these is called viscosity. So viscosity is the resistance to flowing. And a simple way to think about viscosity is how thick a liquid is. And so this picture over here on the right sort of shows this. In this blue container, which is just dyed water, we know that water is very easy to pour. If you turn over a glass of water, it's going to pour out very fast, whereas other really thick liquids like motor oil, for example, if you try to pour those out, it's much slower process, so it has higher viscosity. So the thicker the liquid is, the more difficult it is to pour or flow, which we refer to as having higher viscosity. And the correlation here is also that if you have stronger intermolecular forces, that correlates with a higher viscosity for the liquid. Alright, so the resistance to flow is what's referred to as viscosity. It tells you how thick a liquid is, and the more intermolecular forces you have, the higher the viscosity is going to be. Alright, so let's talk about then a quick example problem. We want to predict which of these three liquids has the highest viscosity. And so we first need to think about what is the strongest intermolecular force that's present in all of these substances here. So the first one is CH3, CH2, 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 CH3. Now this is not going to be necessarily obvious, but one thing we should always remember when we're doing problems like this is that if you have a hydrocarbon, a substance that just has carbon and hydrogen in it, without even thinking about more details about the structure, this is going to be nonpolar. And so the strongest intermolecular force in any hydrocarbon is going to be London dispersion force. So that's the strongest intermolecular force present when you just have carbon and hydrogen. The CH bonds themselves are a little bit polar, but when you have a hydrocarbon, all of those CH bond dipoles, which are small to begin with, cancel each other out. So in any hydrocarbon substance, which is just carbon and hydrogen, you can automatically assume that it's going to be nonpolar. So this one's nonpolar, it'll only have London dispersion forces. But if we go to this substance here, which inserts an oxygen in the middle, if we draw the structure of this, this is going to be a lot like water, but instead of hydrogen, it's going to have just two carbon chains on it, CH3, CH2. So this is going to be another bent molecule, because you have the two lone pairs on oxygen still. And so this is going to be a polar molecule. We have dipoles between carbon and oxygen, a net dipole that then points towards oxygen. So this molecule is going to be polar, but it doesn't have any hydrogen bonds because none of the hydrogens are bonded to oxygen. So oxygen is only bonded to carbon in this case. And so I should probably draw this maybe a little bit more precisely to indicate that. So the oxygen in this case is only bonded to carbon. As you can see, so there's no bonds between oxygen and hydrogen. This is a polar molecule, and so this would exhibit dipole-dipole forces. And then finally, the last substance here, what we notice is that it has two OH bonds. And as soon as you see that there are OH bonds present in a substance, you automatically know that there's going to be hydrogen bonding. That's the strongest intermolecular force of all of these three. And so this substance here, which would be called propylene glycol, I believe, if I got my nomenclature right, that substance is going to have the highest viscosity because it has the strongest intermolecular forces of these three substances. All three of these substances have very similar molecular weights, very similar number of electrons, but we see that the strongest intermolecular forces are going to be present when you have the hydrogen bonding situation, and so that would be expected to have both the highest boiling point, the highest melting point, and in this context of this problem, the highest viscosity. So all of those properties depend on intermolecular forces, and we need to be able to then predict and rank intermolecular forces for different substances. So that's really all we want to say about liquids. As I said, there's not a lot we're going to do with liquids. You just want to know some of those basic properties and how they relate to the intermolecular forces that are present. Now let's start talking about some properties of solids. And before we get into talking about the properties of solids, let's talk about the different types of solids we have that we're going to deal with in this class. So there are two major types of solids that are present. There's amorphous solids and crystalline solids. Amorphous solids are solids that have no regular structure. And so what this means is that in these types of solids, the atoms and the molecules are arranged randomly. Alright, so amorphous solids, you can't really easily predict where the different atoms and molecules are going to be. They're just sort of randomly arranged. It's just a random pile of atoms and molecules. The classic example of an amorphous solid is glass. Now there are certainly many other types of amorphous solids, but we're not going to deal with these a lot because the structure is so irregular, so there's not much you can say about it. And probably the only example that we'll come across that you should be familiar with is glass. Now the other major type of solids, which we're going to get a lot of details on for the rest of this chapter, are called crystalline solids. And so these are solids where the components, whatever the solid is made up of, atoms or molecules, these components are going to be arranged in a highly regular fashion. So a highly regular and periodic fashion, meaning the structural elements that exist repeat themselves over and over again to build that piece of the solid. And so when you have a crystalline solid, there's sort of two parameters that are associated with that structure that we want to be familiar with. The first is lattice. So a lattice is a three-dimensional system of points where each point represents, in a chemical sense, an atom or molecule in the crystal. So the lattice is essentially, it's a regular repeating pattern that extends in all directions for the solid, and that's going to then represent the arrangement of those atoms or molecules in that solid. So it's regularly repeating, it goes on forever in all directions, it's infinitely repeating, and that's what we refer to as a lattice. Now, of course, the thing about lattices is kind of daunting because they go on forever and ever. So what we're going to really talk about and how these structures are usually defined more conventionally is what's called a unit cell. So the unit cell is the smallest repeating unit of a crystal. And then what happens is that the crystal lattice, which we said is that infinite arrangement of all of the units, the crystal lattice is going to be generated by translating the unit cell in all directions. And so maybe a helpful analogy for this would be, building blocks like we played with when we were all kids. So the unit cell would be one of those blocks, and we're going to talk about how a lot of unit cells that we deal with are, in fact, cubic in shape. Those are the ones that we're going to primarily deal with in this course. So you have this unit cell that's a cube that's going to include some number of atoms and molecules inside that cube, and then we take that small cube and we stack it in all three directions to make up what's called our lattice. So we take these small building blocks and we arrange them side by side in all three directions and generate what's called our crystal lattice, which is the infinite array that we talk about when we talk about a crystal structure. So those are some of the definitions that we're going to deal with for crystalline solids. So there's going to be then within crystalline solids a few different types that we'll deal with and some of their key properties, and we're going to get into more details of each of these. So the first one is called an atomic solid. And as the name implies, this is a solid that's made up of one type of atom. And so examples of atomic solids, one that we're all probably familiar with is diamond. So diamond is just a form of carbon. It's a crystalline solid where all of the lattice points are made up of carbon. And most metals are examples of atomic solids as well. So we're going to talk about the structures of a lot of metals as well. And most metals fall into the category of atomic solids. They're a solid made up of only one type of element or one type of atom. Ionic solids is another category we're going to talk about. And so we know what ionic compounds are. And so in an ionic solid, the lattice points are going to be made up of alternating plus and minus ions, positive and negative ions. Okay? So in ionic solids, you arrange the plus and minus charges in a regular fashion. And so pretty much any ionic compound in its crystalline state would be classified as an ionic solid. So we're going to talk about a few different structure types like sodium chloride, zinc sulfide, magnesium chloride, etc. Alright, so these are different structures of ionic solids where again we're going to talk about some of the differences between those and how the ions arrange themselves. And then finally the last type of solid is called a molecular solid. And so a molecular solid is a covalent compound. So atomic solids are typically always elements, ionic solids are ionic compounds, and a molecular solid is a covalent compound where the lattice points are molecules that make up that compound. And those molecules are held together by intermolecular forces. So in a molecular solid, you have molecules, and then you have a repeating array of molecules all held together by IMFs. The classic example of a molecular solid would be ice, which is one that we're likely familiar with. But really, any covalent compound in the solid crystalline phase would be considered a molecular solid. So these are the types of crystalline solids, and we're going to talk about some details of all of them throughout this course. The first type we're going to talk about are metals. And so before we get into the structure of metals, which will come next time, let's talk about a little bit about metallic bonding. And so metallic bonding is a little bit different than what we've seen with covalent and ionic bonding. So metallic bonding is a completely delocalized system. So the key property of metals is that all of the valence electrons are held very loosely. As we know, they have very low ionization energies. It's very easy to remove those electrons and form positive charges. So the electron C model supposes that in a metal solid we have basically a regular arrangement of positive charges. So we're talking about the first column of the periodic table, group 1A. We know that these have one valence electron that's loosely held. That'd be things like lithium, sodium, and potassium. And what the electron C model says is that you have, in these metals, you're going to have electrons that are just delocalized between all of the positive charges. Okay? So you don't have electrons that belong to one atom or another. You don't have electrons that are shared between two atoms. You have this whole delocalized sea of electrons, as it's called. So I want to make sure I clearly define this. What I'm sort of drawing as a yellow smear here is this sea of electrons. So it's these delocalized electrons. All of the valence electrons are kind of shared between all of the atoms in the crystal. They're delocalized, they're freely roaming around, and they're not tied to any one atom or any pair of atoms. And then if we go to the second group of the periodic table, group 2A, which would be magnesium, calcium, and so on, those, as we know, have two valence electrons, so they're going to have two loosely held electrons, and you can think of their bonding then as being a series of 2+ cations. And then in these metals here, you have two valence electrons from each metal that are going to be delocalized over the entire crystal. So the two valence electrons in group 2A metals are also then delocalized into this what we call sea of electrons, freely roaming around the metal, not tied together in any real way. And so that's the key point about metallic bonding. So, covalent bonding, as we said, is sharing of two electrons primarily between two atoms. Ionic bonding is a charge-charge interaction between a positive and a negative ion. Metallic bonding is a bit different. It's the idea that we have delocalized valence electrons. So all of the valence electrons are loosely held and delocalized, and that's what we refer to as metallic bonding. Alright, so that's how we think about bonding in metals. It's not an interaction between two metal atoms, but a delocalized sea of electrons that holds all the atoms together. And so then let's talk about some of the properties of metals that are related to this electron sea, to this delocalized bonding metal, or bonding model that exists. So if we think about the melting points for metals, they tend to be moderate to high. So as I said, most metals exist as a solid at room temperature, and you do have to go to usually relatively high temperatures to melt them. But it's not extremely high temperatures because, again, the forces, there are relatively strong forces involved with this electron C model. The electrons delocalize around all these formally positive cations of the nuclei, but there's still relatively strong forces, and you have moderate to high boiling points. So let's talk about how the melting point of a metal changes with relation to its periodic position. So as you go across a period from left to right, the melting point increases. And that's because as we go from left to right, we know that there's more valence electrons, which means that you have more positive charge at the metal center and more delocalized electrons, which gives you then stronger attractions. So as we go back to this picture we drew up here, in group 1A you have one valence electron from each atom, and you have formally then positive charges at each position, and so you have an interaction between one valence electron and one positive charge is delocalized. In group 2A, you have two valence electrons, so you have higher positive charges at each center, 2 plus charges instead of 1 plus, and because of the higher charges, you have stronger attractions between the electrons and those metal atoms. So as you go across, especially when you're comparing group 1A to group 2A, the melting point tends to increase. So if we compare sodium and magnesium, which are right next to each other, magnesium has a much higher boiling point than sodium because it's to the right on the periodic table, and it has more delocalized electrons that hold the atoms together more strongly. Now as we go down a group, down a column of a periodic table, the trend is opposite. The melting point decreases. And that's because as we go down the column, the metal ions become larger. We talked about the trends for ionic radius a long time ago. And when you have larger ions, you have weaker attraction to the electron C. Alright, so melting point decreases as we go down because in the larger ions they're going to be less strongly attracted to those delocalized electrons. Because remember that the attraction between oppositely charged species is a function of both the distance between them and the charge. And so if we go down the periodic table, the distance between the charges increases and the attraction between them decreases. So those are the melting point trends. If we talk about the boiling point for metals, those tend to be very high. And that's because it's difficult to completely break those metallic bonds. So it's difficult for the cations and the valence electrons to completely separate from each other. So you have to go to really high temperatures to be able to take metals into the gas phase typically. And that's because with this delocalized sea of electrons, they're holding all the atoms together and preventing them from breaking apart from each other. Okay, so melting metals is not terribly difficult because when you melt a metal, the electrons and the nuclei are still in contact with each other, so this delocalized bonding is still going to persist. But when you want to boil an element, a metallic element, you have to separate the atoms completely, and that completely breaks all of the metallic bonds. All right, and then one last thing we'll talk about relationship to the properties of metals are their mechanical properties. So we haven't talked about mechanical properties yet, but these are essentially the behavior of a substance under physical strain when you put pressure on the substance, when you bend the substance, when you try to break it, all these different things related to the physical properties as it pertains to the strength and the mechanical aspects of it. So if we talk about the mechanical properties of metals, the key point about metals is that they're malleable. And this is one of the most important properties, and this is why metals are so widely used in constructing buildings and bridges and things like that, because they are bendable, which means that you can mold them into any shape. You can put a little bit of strain on them without them completely breaking. And the reason for this at the atomic level is that metal ions are not really held tightly in place, all right, because the electrons are delocalized. There's not really a regular electronic structure. You just have this, as I said, random sea of electrons that's sort of keeping everything together. And so it's possible to move these atoms around, to slide them around a little bit, to bend them, to change their positions without completely disrupting that metallic bonding. So these metal atoms that exist in this electron sea, because they're not really tightly held in place, they can slide through the electron sea, and that is then responsible for the ability to bend and mold metals that we have, their malleability, as we say. Alright, so metals are able to be bent because the individual atoms that are in the metal can sort of move around within the electron sea without completely disrupting the bonding between them. And then, as you also probably already know, metals have very good electrical and thermal conductivity. So both for electricity and heat, metals are good conductors, both in the solid and liquid states. And that's because the electrons are mobile. So this delocalized sea of electrons, as I said, they're not held in place between two atoms, they're not held in any one location. And so because you have this high electron mobility, especially for electroconductivity, it makes sense then. Because the electrons are mobile, you can pass electricity through metals very easily. The electrons are not tied in place, and they can flow through and conduct charge that way. All right, so that takes us to the end of what I want to talk about today. Again, just some basic definitions and concepts to get us started when we talk about condensed phases. A lot of what we're going to get into in the near future now is going to deal in more detail with the structural aspects of solids, especially metallic solids and ionic solids, where we talk about, again, the different ways that the atoms and the ions can arrange themselves regularly throughout the crystal. Now, obviously, because this is a virtual lecture, you couldn't ask me any questions during the lecture. So if you have any questions about what I talk about today, there's a few ways you can get those answered. You can either send me an email, you can come see me in my office whenever I'm back, or alternatively, if you leave the question as a comment on the YouTube video, I'd be happy to answer it there for the benefit of everyone that can see it. So thank you for tuning in, and thank you for listening to this, and I will see you guys back next week when I return.